All right, students, so here we go. We are going to look at Millikan's oil drop experiment. And so we've already discussed a lot of the theory, a lot of the things that come before it, but now we want to actually perform the experiment. So two of the things that we want to do is you want to make sure that you bring down the video. So this is the Millikan experiment, and I have version 2.1. So, and we're going to go ahead and bring down the calculator. So I shouldn't do it like that. I want to bring it down from the cloud. And so we'll come back and get that. I want to take the experiment over first to video physics, just like we do at this time. And you'll see that we have something looking a little weird, but it's all good. So let me go back and label this. This is experiment number 3, and I'm going to call it Millikan. That'll be enough. Okay, it's already taken. So about Millikan oil drop. All right, that works. Basically, I've already done it or something like that. So all right. So the first thing, of course, that you know what, it's set up and it's set up. So let's go ahead and get the calculator and let's put it into the folder here on Dropbox. So just gonna go ahead and upload this. So I'm going to duplicate and I'm just going to call this Millikan calculator. And I want to make sure that I put it in Dropbox. And let's go on over here. Let's go down. Millikan and duplicate. Okay. So basically what we're about to do is we are going to track an oil droplet inside of a closed chamber. And so you know that I have those two plates that I spoke about in the theory. One is ground, it's at ground voltage or 0 voltage, and the other one is going to be either plus or minus 500 volts. So we're going to find the rise and fall velocities here, and the average rise and the average fall velocities will be calculated. So our main goal will be to do this. The radius is going to be calculated with this calculator. And so if you look here, we have a constant here. This is just a constant out of the lab. And then we have atmospheric pressure. This is, remember we talked about pressure inside of the classroom. So this is newtons. That's your perpendicular force over your area, okay? Over the area that the force is applied to. So that's meters squared. So our atmospheric force on that day, which was, we did this at I did this at 9:36 a.m., March the 10th, 2016. And the atmospheric pressure around that time was 102,000 pascals. So it's 102,218.12 pascals. That's what this unit is. So I could have just put in a PA. And then we have eta here. This is viscosity. So the viscosity is going to be determined based on the temperature inside of the chamber. We use what is known as a thermistor. It's like a resistor, but it's a thermistor, and it allows us to take temperature readings based on the resistance going through that thermistor. And it's coming out to be 1.84. Oh, no. The temperature was 25 degrees. So the thermistor was 1.98 mega ohms. That is corresponding to 25 degrees Celsius, and I'll show you these charts in a little bit. And when you look on a chart for viscosity of air, inside of the chamber, it's coming out to be 1.84 e to the negative fifth. So this eta here is viscosity. I should have just written viscosity here. You know what? I mean, I could change it, but it's just viscosity.